Okay, hi. My name is Eric Toon. I'm here with my colleague Dominik Marcinski. We're both at Google, and we work on GKE and Kubernetes. And we're going to talk about multi-host inference training. And so, in our work, we've had the opportunity to work with a number of customers that do fairly large-scale AI workloads. And we'd like to share some of the use cases we see, and then what each of those use cases has some different implications for scheduling, and we'd like to share where we think that should drive scheduling in Kubernetes. So the first case we see is pre-training, and I'm going to assume kind of a very basic level of knowledge here. So with pre-training, you're trying to create a new model. And so these are the largest size workloads that we see. They are almost always they're always multi-host, and they're usually even multi-domain, meaning that multiple racks or NVLink domains are involved. They're just the largest amount of machines the customer can acquire. And then after some initial training to get started, like experiments and trials and tests, they're going to run as large as they can for days or weeks at a time. So the biggest challenges we see in the pre-training workloads is to detect and restart quickly after there's either a software hang-up or there's a hardware failure. With so many devices being used, there can be hardware failures every couple of days. And the time that it takes to recover and restart is significant reduction in cost. In the reduction in the value they're getting out of the machines they've already purchased. So when these hardware failures happen, there's some level of coordination needed with the application to tell it if it needs to restart because it has a fixed size. That's the most common case. But we're starting to see some applications that run frameworks like Torch Elastic and Monarch and JAX, and those actually allow the program to continue running without restarting while replacing a small portion. So if you have 10 racks, you could lose one rack, and that's actually able to keep running. And then later, when you maybe physically repair that hardware, it can rejoin the application. And so that's kind of an orchestration problem the scheduler would need to be involved in as well. Once you've got a model, it's able to chat with you, but it may not be smart about specific subjects like how to program or how to do math problems. So you can't really make it better at programming by just practicing predicting what is the next token in this program. You need to let it generate a whole program and then compile it and see if the answer's right, or solve a whole math problem and then check if the proof is correct for the math problem. So that idea of running way ahead of the next token and then deciding if it's correct or not later, that's reinforcement learning. And so we're seeing a shift to a lot of people doing there's lots of different post-training activities and fine-tuning, and hear about RAG and LoRa, but we're seeing reinforcement learning being the main thing that happens. And so it's definitely going to be multi-host because you have to be able to back-propagate through these models, and it can even be multiple domains of machines. And it's less clear what the duration is. There's multiple ways to do this. But one of the key challenges we see is that you have both accelerator workloads and CPU workloads, and they need to be running at the same time and closely interacting, but they may be on different types of hardware. So, for example, you need the accelerator to make an inference, and then the CPU says, okay, was that a good math solution or was that a good program you wrote? And then you need to go, if it's yes or no, you need to go propagate back through the model and say, okay, good job or bad job. And the other challenge we see is that people are writing a lot of these reinforcement learning programs using frameworks, especially Ray, that want to be able to dynamically create and resize pods and have a lot of dynamicity. And so the scheduler, what's the role in the kube scheduler if Ray is making a lot of decisions on its own? So once you've got this model pre-trained and post-trained, then you want to use the model, serve it and make some money off all this money you've spent to train it. So large models these days are going to be multi-host for the minimum small sort of serving footprint as you've tuned it. You could run it really slowly, but usually the amount of memory that you need, including the memory in the GPUs, that's going to kind of determine your basic footprint or a replica. So here, replica used to mean like pod in deployment or stateful set, but here replica mean like n pods in a certain configuration. So when you scale up, then you're going to add more of these multi-pod replicas. So that's kind of a new pattern that doesn't exist in the scheduler, so that's one challenge. And another challenge is that if you have like the online inference, like coming from customers, it's going to vary throughout the day. You don't want the machines to be idle, but you do want to be able to respond to like spikes. And so like this mixture of like running lower priority work plus this complexity of this like multi-pod replicas and scale up and scale down, that's a challenge. People also fill in these troughs with like batch inference, which is where they maybe come in through the load balancer, but they're willing to tolerate a longer latency, but maybe you don't have enough of that type of work. So then the fourth category we see is research. Like you've got, the first three were like a production cycle, and this is more like how do we generate new ideas for what we're going to do for the next production cycle. So you generally have a bunch of researchers, so they need to like fair share between the machines. They're running smaller workloads, so you maybe need some kind of preemption to use all the resources well and manage fragmentation when you've got a bunch of different things running. So what are the implications for scheduling? I took all the challenges things I just talked about in the last 4 slides, and I grouped them into like, I think 4 categories. So like higher throughput, orchestrating with applications, being aware of like workloads, groups of pods, and topology, groups of nodes. And then like the need to be able to extensibility. So because we see that customers want a lot of control over what exactly fair sharing means for them. So like, how do you deal with all these different things we need to change at once? So there's, stepping back, there's a basic assumption that I won't like go into a lot right now, which is that, solutions for all these problems exist in the broader Kubernetes community, but it's like, we think we want to have it in the core to solve a lot of this stuff. How do we attack this? So I kind of put all the colored boxes are all the challenges with the 4 workload types that I mentioned before, and then the gray boxes are like ideas about capabilities that a scheduler could have. I don't expect you to absorb all of this, but like one observation is that like, where should we start with this? So my view is we'll start with the gray boxes. Those are capabilities that have the most use cases that kind of depend on them, and try to make progress on those. And so the gray boxes with the most in edges is like pod groups and node groups. So what does it mean to like group pods and group nodes in the scheduler? Like what am I talking about? Someone who knows much more about the scheduler will give us the next level of detail. Thanks, Dominik.
Thank you, Eric. How to move the slide?
Spacebar.
Oh, maybe. Okay.
I don't know why it's slow.
Okay, it works now. So we are aware that we need to run various combinations of the workloads that Eric was talking about, even in a single cluster. So people expect that Kubernetes will handle those situations well. So why to improve kube-scheduler? We could say that there are many schedulers that are capable of scheduling workloads already, and that's true. We believe that Kubernetes extensibility is a great value that we want to preserve. But at the same time, the problem is that workload scheduling is not sufficient. We need to protect running workloads, and we need to assure their integrity. That's why we need to make many components workload aware. So we introduced the workload API in which we can model workloads. In this way, kube-scheduler should be able to schedule such workloads. And that means it needs to support workload level scheduling constraints like topology and all or nothing requirements. So what changes are needed? We need workload awareness and we need workload scheduling. Those are two different things that we need to understand what's the difference between them, and I hope to explain it in next slides. Kube-scheduler will do both. Workload scheduling will be fully customizable. So you should be able to extend kube-scheduler using a plugin framework. And we could even say that workload scheduling would be completely optional because users may decide to use external scheduler, and those external schedulers should be seamlessly integrated with kube-scheduler. So what is workload awareness and why we need that? So each component which affects some pod scheduling needs to be aware of workloads. It needs to know that the pod is a part of a workload. So anytime the pod is affected, the whole workload is affected. So to know how the workload is affected, we need to reflect that information somehow in the workload. But to really assess what is the impact of some change, we need to involve scheduling. And scheduler needs to try to reschedule workload, meaning it needs not only to consider the scheduling constraints, but it also needs to consider the current workload state. So it should tell us whether it's enough to reschedule just a part of a workload, for instance, move a single pod elsewhere, or the whole workload is affected and needs to be stopped. In that case, we lose the time and resources that the workload spent from its last snapshot, for instance. By the way, it's a good example of what kind of information we need on a workload level. It may be no longer static information. It might be dynamic information, like when the last snapshot was taken. So what changes we need? We need to extend kube-scheduler to accept workload placement proposals, either generated by the kube-scheduler itself or coming from the external schedulers. It has to do it atomically to avoid deadlocks. It needs to coordinate binding in all or nothing fashion. Whenever this actuation process fails, it has to trigger workload rescheduling. So it needs to consider the conditions that lead to the failure, and rescheduling should produce a new plan which is supposed to succeed. Rescheduling can be triggered also in case of preemption or cluster state changes, in particular hardware failure. So what's the workload scheduling then? We expect that at some point every pod will be part of some workload. In the simplest example, pods will be just grouped in workloads, and they will be still scheduled individually like it is today. So the value is when we have some workload level constraints. At that time, it means that pods cannot be scheduled individually, but they have to be scheduled all together in a consistent cluster snapshot. Some scheduling constraints may require to consider various combinations. So it makes the workload scheduling pretty complex problem that may take time to resolve. But we don't want to solve the NP-complete scheduling problem. So we are thinking how to simplify the problem, how to find the algorithm that can do workload scheduling in a reasonably short time. Because the overall, if we want to have some price performance gains, we need to consider multiple workloads in some scheduling simulations. We assume that it will be orchestrator components which will do such what-if simulations, but hopefully they will be able to use kube-scheduler workload scheduling capabilities to not solve the problem of workload scheduling in many places. So what changes are needed for workload scheduling? In kube-scheduler, we need to add a new phase that will allow to schedule multiple pods together in a single cycle. And we finally need to develop an algorithm how to do it effectively, because it's no longer scheduling a single pod, it's scheduling of a tree-like hierarchy structure of pods, like pod group, like what Eric was talking about. So we can now take a look how the scheduling framework will change, and I hope it will also explain what's the difference between workload awareness and workload scheduling. So currently, each pod is scheduled one by one. So the binding directly follows the scheduling phase. In workload-aware scheduling, we want to clearly separate logical scheduling from actuation. So we want to first collect changes and accept them at the same time before we allow actuation. But the actual workload scheduling will happen earlier. So it will be a new phase in which many pods are scheduled at the same time. Interesting is the fact that the output of this phase will be something like a placement proposal. So very similar to what external schedulers would produce. That means that in both cases, it has to go through the workload-aware acceptance phase in scheduler, so that kube-scheduler is able to resolve the race between itself and between other schedulers. So once the proposal is accepted, the actuation can follow. So in this case, the scheduling that we understand today remains just like a validation, and the workload scheduling would happen simply earlier. Right, so that's all regarding the introduction. We accept questions.
Hi, thanks for the presentation. Do you have an example of what one of these workload objects is going to look like?
Yeah, it's the API merged it'll be alpha in 135.
Okay, yeah.
So, but I'll give you a quick overview. Top level object has a workload, then a workload, so that means like all of the pods that belong to one, what I call a true controller. That could be any of like the tens or hundreds of different controllers that have been written for Kubernetes. So there's a one-to-one mapping between the kind of the top level controller, like a job set or a leader worker set, or it could just be a plain deployment, right? So those have like, sometimes the controllers are stacked on other controllers, like deployment is stacked on top of replica set. But the top level one that you want to schedule, that's a workload. And then within there, you can either describe the workload as consisting of like a single gang of pods that need to all be scheduled at once, or there can be multiple named gangs that corresponds to something like job set, where you have replicated jobs. Or you can say like, I don't even know how many I'm going to have. I'm not going to tell you. They're going to scale. That would correspond to the inference use case. So you have this choice between a single enumerated multiple or unenumerated multiple gangs of pods, and there's a way in the pods to specify which of those groups they belong to. That's what's in 135. We'll also have ways in the future to like give more detailed specifications about how you would like pods to be ranked or enumerated, and how like what their resource requirements are.
Is it like a pod template, like you embed the pod template directly in the workload object? Or?
That's not in 135, and I don't think we will verbatim include pod template. I think we will give some thought to like what are the fields that are relevant to workload and what are fields that are not. So for example, I think we need to define that like environment variables are not scheduling relevant. And if there's some plugin that like wants to look at environment variables to look at like to make a plugin decision, like that's too bad. Mm-hmm. So some subset of what's in a pod template, and maybe also some things that are not in pod template. Like maybe you want to be able to have a workload describe future like vertical scale up requirements, so you could not only have current resources, but like requested ability to scale up to future resources.
I guess I'm just confused as to how you put it all together then. So you have to create a workload object first, and then name some pods.
Yes, there's two main workflows. One is where the not preferred workflow, but that is available, is the user makes a workload, and then they embed the name of the workload in their pod template of their true controller. The preferred one that we've got embedded in 3 workloads for 135 is that the workload controller knows how to make workloads in parallel with pods.
Mm-hmm. I see. So in the first one you said, it's the reverse of what I said. You create a workload object and then you reference that in the pods. And so when the scheduler sees there's a pod coming in that references a workload, it knows to wait, I guess, until other pods that also reference the workload show up.
It always does what you said. The scheduler always, if it sees a pod that all pods that have workloads have in their pod specs something that says, I have a workload, here's what it's called. Mm-hmm. The distinction I was making was between like a manual flow versus an invisible to user flow of workload.
Okay, yeah, that makes sense.
Happy to follow up, give way more detail afterwards.
Yeah, I'll also be there tomorrow.
That'd be great.
Yeah, great.
But I think at some point it would be great if we could schedule workload even if there are no pods yet. We are not certain how exactly to do that, but that would be the desired state.
Yeah.
Can you talk about what you have thought about in terms of mutability?
Yes, we are sure we'll need it. For 135, we kind of stepped around mutability by saying it's immutable, but we allow dynamic discovery of gangs in order to support leader worker set. And we feel like this is good enough for us to get a lot of exposure at alpha. And then we need to prioritize what mutations will allow. Probably we need to allow people to like add another gang to a workload. Since we haven't added any of the real detailed pod template stuff, I think there's a discussion still to be had about what part of that is mutable. It definitely is going to get complicated.
Yeah, for sure. Like, will we forbid things like HPA, VPA references to pods that exist within a workload?
No, but I think like one that is not part of the main like AI thrust of this, but off to the side, is that we don't have a way for a VPA workload to say, hey, these are my current requirements, but I have a pretty good idea that like with 95% probability, I might need to go up to this. And have the scheduler be like, oh, well, let me try to find you a place where there's something lower priority than you or whatever, where you'll have room to go up. Or to coordinate with cluster autoscaler to say, like, let's not put this guy on a node that like there's no like cloud provider scale up available either. That's not a priority, but that is something I think workload's a good home for.
For HPA also, you can't right now just specify gang size. So trust me.
Yeah. So right now,
It's almost like the HPA would make an update to the workload at that point.
So I'd say that workload, so a plain deployment would not ask for gang scheduling, so it would not need to specify the min number of nodes. It could just say, hey, I'm a deployment, I'm a workload, I'm not gang scheduled, but please know that I'm a workload. And then it would not have to specify a minimum, and it could scale as much as it wanted.
Why would you say your workload? What do you get if you're not being gang scheduled?
Okay, not everyone agrees that this is important, but I think I'd like to be able to say kubectl get workloads and then see every kind of workload in my cluster. And then maybe be able to like join that with their node use, like see aggregate usage. And so I felt like that's a missing concept in Kubernetes for a number of years. If you look at something like Slurm, like or most other schedulers don't start from pod. They start from like, here's the predefined set of workloads. The fact that Kubernetes lets you extend workloads has been amazing. If you look at every year of the history of Kubernetes, you can see that like a new workload was added kind of that year that really changed, expanded the capabilities, whether it's adding stateful set or adding job set or any number of other things. So extensibility is important. We want to keep that. But we also need standardization for the scheduler to be able to like make sense of all the workloads that are out there. I'm not sure I answered that well. But.
I think I get the gist.
Yeah, my question is about the preemption of a workload is no longer 0 or 1, it's rescheduling. So my question is that why do we need to reschedule? For example, if I don't have GPU, so even I reschedule, I still cannot get enough GPU. So in which cases should we consider rescheduling the workload?
So I think we will have many different types of workloads. So some of them may be rescheduled partially. So if we have a serving workload, then rescheduling a single pod is possible. But if we have a workload that has a gang and all or nothing requirements, then definitely rescheduling needs to still satisfy those requirements. So it may be not possible to just reschedule a part of it.
Gotcha. So basically the difference that previously we reschedule the whole deployment, but now we can do partial reschedule. For example, if I have 10 nodes, and for each node I have 1 pod, so I can only reschedule 1 pod instead of reschedule 10 pods.
So currently we reschedule pods, but those pods are also part of some workload, even though we don't call they are part of a workload. So once we know that they are part of a workload, we may know better how to do a preemption of a single pod and how it impacts the whole workload. So depending on the type, it will be possible or not.
I see. Also, I have a question about the background. So beginning, we mentioned about that we have 3 different tasks, pre-training, post-training, and inference. So what are the difference between pre-training and post-training? The major difference?
Are you asking like what is it from a machine learning standpoint, or what is it from a Kubernetes scheduler standpoint?
Kubernetes scheduler point.
Okay, so because pre-training workloads tend to be running at the highest priority, then we're not really interested in worrying about something preempting them. And they almost always use every accelerator on any node they take, so we're not interested in bin packing them. So we can imagine doing simplifications when you're not worried about prioritization and bin packing. And the goal is to like absolutely minimize downtime when there has to be a pod deletion and recreation cycle. So we could use those restrictions to also accelerate that. If we have 300 pods per second as a goal for the scheduler, and you're running something that has like thousands and thousands of pods, you would like to not have the several tens of seconds of downtime as you bring it up again with a new image or like restart it after a hang. That concern doesn't exist as much with pre-training with reinforcement or post-training, because as I understand it, it can often be broken up into smaller jobs that have independent failure.
Yeah, I have a similar question because previously we mentioned 3 different tasks, but later on our framework is only 1. So we meant that for the pre-training, our focus is about the priority. So the priority for the post-training should be very high, so no one can interrupt the training job. what are the key priorities for the post-training and inference in our scheduler framework?
So in my opinion, the challenges are dealing with heterogeneous workloads, both accelerated and non-accelerated need to run at the same time, and supporting frameworks like Ray. Though to me, in my working with customers, those are some of the key challenges that came up. I'm not claiming to know exactly what the framework is to deal with post-training, and I'm not trying to build the Kubeflow project has named components that deal with different stages. I'm not trying to encroach into their space of having a more highly opinionated definition. I was more trying to give a very vague definition to maintainers that maybe weren't even thinking about these concepts. If definitely we could go further with that. I don't want the core to do that.
Got you. My last question about the scheduling hierarchy, like a tree structure. So why do we have a tree in the scheduling there?
So pods will be grouped in groups, in gangs. Those groups may be grouped together as a group as well. So in fact, it will create some hierarchy which we need to schedule as a whole. So we need to consider scheduling it on every level of such hierarchy. It has to be feasible.
Yeah. So you could think about a cluster that has nodes, and then the nodes are on racks, and then the racks are on bigger switches. So you have often have a hierarchy of hardware. And so a high performance workload, the person is thinking about that hardware, communication costs differing. So then they group their pods or the portions of their application to kind of fit into the hardware hierarchy. So there's an assumption that the user has created a pod hierarchy to match a presumed hardware hierarchy. So the scheduler's job, at a very coarse speaking, is to match a hierarchical collection of pods with a hierarchical collection of nodes, except they may not exactly match because there's hardware failures and multiple things running. But it's kind of a fuzzy match between these two hierarchies.
Thank you.
I'll just ask the question I originally was thinking, but so many more have come up since this discussion. But what is it only used during scheduling of when a pod is trying to be placed onto a node? Is it ever used at any other time?
Are you asking about the workload resource that's in 135?
Yeah, well, not necessarily 135, what the intention is.
Okay,
Is it
so
using descheduling?
the most important consumer, in my opinion, would be kube-scheduler. That's where we're planning to do implementation. If someone wants to write their own scheduler from scratch rather than using a plugin framework, they're welcome to use that. We are inspired by the workload resource that's in Q and expect that it would be able to have some of the same capabilities. So that'd be an example of that. I also think that cluster autoscalers will want to be able to interpret this resource because they will understand can I provide a bunch of random GPUs that are in different places in the data center to meet these 10 pending GPU pods? No. So it will have to interpret that to work correctly. I think over time, maybe even accounting, many other programs will discover those cases where they want to understand workload. I mentioned having it be a UI concept where you could list all my workloads. So if your workloads have 1,000 pods in them, kubectl get pods, not that interesting. Get workloads in a research cluster, pretty interesting. That's matching a Slurm type of use case where you list jobs. Q, Volcano, frameworks like that do provide a job level view, but they don't always handle, I say, long running workloads well. So if you have a mixture of inference and jobs, I think kube-scheduler is the point where you maybe manage both of those. That's a debatable point.
So if the workload is evolving over its period, maybe it starts with a certain number of Is it a mutable concept?
Yes.
Is it a metadata concept?
There is a design doc which explains what we call API Rev 1, which is in 1.35, and then we talk about API Rev N, which is here's what we think it could be in a year and a half from now. So that's in a doc which is linked from the workload KEP. I apologize that it's 80 pages long, and I'm happy to give you a medium answer afterwards.
Yeah, thanks for the great presentation, by the way, for the overview. I have, I think, 3 questions. So the first one, on the slide, you mentioned that the workload API will expand to support topology-aware scheduling, support other capabilities. What about multi-cluster? I know Q has this capability to orchestrate workloads across multiple domains.
Okay, we're
Do
getting
we-
to my expansion and multi-cluster answers.
Yeah.
Will be into my opinion. Feel free to jump in too.
Yeah.
They're like,
Okay.
what's in 135 is like a consensus that was built in the SIG scheduling. So I think I can talk about that as like being a community decision. Now we're in like, what's my opinion? Not like a multi-cluster scheduler like multi-queue or another scheduler could use the workload resource or could translate its internal representation to workload to integrate with a scheduler. But I don't personally have any plans to like make a workload resource-based multi-cluster scheduler. It's interesting. I don't know that it's not a personal priority.
Yeah, that makes sense because I guess like the question would be, there will still be a place for Q to have this multi-cluster orchestration because we see many use cases when this is useful, right? So, but for workload, it's specific to the single scheduler, right? Where Kubernetes cluster control plane is running,
Yeah.
correct?
Yeah.
Makes sense.
And we're definitely inspired by like Slurm, Q,
Yeah.
Volcano that have solved all those things. We're trying to take little bits of what's the consensus about and pull it into the core.
Yeah, that makes sense. Another thing about external schedulers, right? You talk about Ray, Torch has rendezvous. So how we envision those schedulers work together? We have Torch, Jax, other part of EI ecosystem, which has its own way to do the things, and we also have schedulers.
So ideally, the kube scheduler will provide at least the lowest level of keeping track of resources allocation, validating whether the placement is basically correct, it's valid, it's up to date, and it should provide also atomic acceptance of workload placements to avoid races if we have multiple schedulers, workload schedulers, because otherwise they may end up in a deadlock.
Should we talk about reservation or not?
Not necessarily, not in this context.
Okay,
I
sounds
think.
good.
So I guess like, correct me if I'm wrong, but the main idea is to give capacity for those workloads to run efficiently, right? Because those schedulers, like what would be the goal for our scheduler and those external schedulers like Torch, right, with their own orchestration? How they work together.
Okay, so there's schedulers work at different time scales,
Yeah.
right? Like the Linux CPU scheduler makes decisions so fast that it's called a scheduler, but it's not the same as Kubernetes. So like Ray works at a different time scale, but it does. But if you want to have your cluster be administered by one administrator and you have Ray and something else, the administrator is probably going to want Ray to like interact with kube-scheduler to provide an overall collection of resources. So how do you have things that work at different time scales collaborate? I'm being told I have 0 seconds. I'd be happy to find you after.
Yeah, makes sense. Yeah, because Slurm, for example, right? Slurm has its own skill. How we can make sure this run efficiently. So it's a question.
Thank you very much.
Yeah. Thank you.
Yep.